Hello, physics students. Today we're going to examine how the force of friction works. I'm going to start with this simulation from the PhET website. A link to the simulation is in the AP Physics Resources site. PhET contains lots of simulations for both physics and chemistry and is incredibly useful for exploring physics and other topics. So what we have here is we have a crate, and we're going to push crate, see how the force of friction changes. Now, right now, we're not pushing the crate at all, and so there is no force of friction. Friction will only exist if we try to move the crate. So let's apply a force to the crate. I'm going to also allow us to see the sum of the forces and the values. So I'm going to apply a force to the crate and watch what happens to the force of friction. So right now, there is no friction. I apply a little force to the crate, and notice the crate is not moving. The sum of the forces is equal to 0. So right now I'm applying 30 newtons of pushing force, but the friction force is 30 newtons in the opposite direction. If I continue applying a force, so at this point I've applied 86 newtons and something odd has happened. Unlike other forces of friction, other forces we've examined, friction will change depending on the situation. So here I am applying 84 newtons of force, but the friction force is matching it and canceling it out. Now, this is due to the fact that the surfaces are locked together. The crate and the surface the crate rest on actually lock together like puzzle pieces. Until we apply enough force to break those pieces apart, the crate will not move. Now, something interesting will happen, though, once we do break those apart. Now, again, I will apply the force, watch the friction force carefully. So we are still not moving. Our forces are balanced, still not moving. Friction force is up to 104. Still not moving. Friction force is up to 109, 114, 117, 119, 124. Now, suddenly, look what happened. Now we are in motion. That is, we are actually accelerating because I have a net force of 35 newtons. That's because the friction force has suddenly dropped down to 94 newtons. It was well over 100, but once we broke those surfaces apart, then the force of friction dropped down. And in fact, it will not change. If I increase the applied force, watch that the friction force no longer changes. As I increase the applied force, the friction force is staying constant at 94 newtons. So let's examine why friction works the way it does. So let's start with a crate here with no forces acting on it. No one pushing it, at least. There, of course, are some forces acting on it. And so if we actually diagram the forces acting on the crate, so the only two forces acting on the crate now, would be the normal force and the force of gravity. And these would be equal and opposite because the crate's not in motion. Now, right now, there is no friction. There is no friction because we're not trying to move the box. All right. Now, however, this box is locked in place. Right now there is no friction, but the two surfaces as they rest kind of interlock like puzzle pieces. Now, but if I went over here and actually graph this force, I am not applying any push right now. There is no force of friction. So right here, my graph would start here. Now, and just for good measure, let's note that there is no acceleration. And there is no velocity. All right, well, now let's say someone tries to push the box. If we try to push the box, as we try to push the box, that adds another force onto the box. So if we take a look at this now, Of course, there is still the normal force pointing upwards. and there is the force of gravity pulling down. But now there is this applied force. We can call it, we'll call it F push. But it's only a small force at the moment. All right, well, clearly, if this box is not moving, if the velocity remains 0 meters per second, and thusly the acceleration is also 0 meters per second squared, then there must be a force counteracting this push. And that force is known as friction. In fact, friction has to be exactly the same size as this pushing force at the moment. Now, the reason why friction exists is what's happening microscopically at the interface between the surfaces. If I could zoom in on just this small section and I could look under a microscope of what was going on between these two surfaces, what I would see is there is no smooth surface. What I would see is a jagged surface due to the box and an equally jagged surface due to the floor. And these two surfaces are locked together like puzzle pieces. So we started with no force friction. And then as we applied this push, friction matches equal size. So for the beginning of the force of friction, it will keep pace and be exactly equal to whatever the push is. Now, we call this type of friction that opposes the start of motion, this is known as static friction. Static friction opposes the start of motion. Now, the reason why the box is not moving yet is because we haven't pushed with sufficient force to unlock these two surfaces together. As you continue to force, as you make this push larger, then eventually these two surfaces will separate, and then something odd actually happens. So let's say you've pushed hard enough to break those surfaces apart. Then then what will happen is the box just doesn't start moving, it will actually start to accelerate. So now let's say that we'll end up with a V in the positive direction, and our acceleration will also be in the positive direction. So what's happening with the forces now? Well, what's happening with the forces is, of course, we still have a normal force. We still have the force of gravity. We now have a much larger push. But depending on the nature of the surfaces, depending on the how smooth the ground is, how smooth this box is, we have a force of friction now, but it actually decreases in size. So what has happened microscopically, if we could again magnify the surfaces between the box and the floor, what we would see now is these two surfaces would be riding on top of each other. So I'd still have the box here and with its rough surface, but now it would be separated from the floor. And the box would be riding across. So you still have a rough surface opposing the motion. You still have these two rough surfaces, but once you break the pieces apart, you no longer have to push quite as hard to keep the box moving. So assuming you were pushing hard enough to break it apart, the force necessary to keep it moving will always be less. So what happens is you'll notice this behavior. So as you increase the push, the force of friction would get larger, larger, and larger, and larger. And then suddenly it would drop off. Now, we consider this two different regions of friction. Why friction is getting larger and larger opposing your push, this is the realm of static friction. But once you break the surfaces apart, you're now in the realm of kinetic or sliding friction. Now, the force of friction of static friction is always going to be greater than the force of kinetic friction. At best, it could be equal, but in no real case is it really going to be equal. So we say that the force of static friction has to be greater than or equal to the force of kinetic friction. Now, something odd happens. That once you enter the realm of kinetic friction, not only does it become less than the static friction value, it is a constant value. That is, once these surfaces are separated, it takes the same amount of force to keep them moving. Now, the reason why you accelerate at the moment the surfaces break apart, because static friction is larger, so it's harder to break the surfaces apart. So once those surfaces break apart, then you are now pushing harder than necessary to make the box move, and so the box accelerates. You will feel this in real life. If you've ever tried to push a heavy box across the floor or maybe move a dresser, you have to push very hard to get it to start moving, but then suddenly it'll lurch forward, because once you break those surfaces apart, you are now applying more force necessary than to make it move. So normally what you would do is you would decrease the force of friction so you can move at a constant rate. So let's take a look at our last picture. So if I want to move without acceleration but maintain a constant velocity, so if I want my acceleration to be equal to 0 meters per second squared again, but I want my velocity to continue moving to the right, that is, I want the box to continue to move, then let's take a look at the forces. Then, of course, I will still have the normal force. I will still have the force of gravity acting on the box. But now I've decreased my push to exactly match the force of friction, the force of kinetic friction. So on our friction graph, again, the force of friction will increase until I break the surfaces apart, and then it'll drop down to a constant value. So this constant value is the value of kinetic friction. And it's unique for any surface and an object. There's no way to actually predict it, so we have to measure it empirically. That is, we have to measure it experimentally to find out what the value is. Now, so the force of friction depends on, well, one, the roughness of the surfaces. The rougher the surfaces are, the larger the force of friction is. This is described by a parameter known as the coefficient of friction. Given by this funny looking m, which is the Greek letter mu. Now, the other thing the force of friction depends on is how tightly the forces are being squished together. That means it depends on the normal force. The tighter the surfaces are pushed together, the more normal force you have pushing down into the floor. And so we can summarize this as that for friction, the force of friction is equal to this coefficient times the normal force. And again, there's nothing magic about this coefficient or mu. This has to be measured. It has to be determined experimentally. Now, but again, we could also break this down that there is both a force of friction of static, which will be equal to mu of static friction times the normal force. Now, in this case, that means that mu is changing size. So the interesting thing about static friction is mu can be equal to 0. That is, I'm not trying to make the box move at all. But it must be less than some maximum value. This is when the box begins to move. Now, kinetic friction will be equal to, again, a coefficient of friction times the normal force, but mu k will be constant for any pair of surfaces. So there you go. So static friction is the trickier one to deal with because static friction can change size depending on the situation. But once you break those surfaces apart, then you're in the realm of kinetic friction, and that coefficient does not change.